Well, thank you, Chen Hao, for the kind introduction, and thank you for having me. So I decided to change the title of my talk to make it a story of planning and control. So hopefully it will give some perspective, and I guess where I think machine learning should uh, go more. Let's see how it rolls out. I hope you enjoy, and please feel to ask me questions as we go along. So, I mean, we have all seen these amazing videos of these humanoids doing amazing things. Now, these videos work, or these robots work in these specific scenarios, and these were built using model-based systems, which were quite engineered by humans. Now, what do I mean by this? Typically, if you want to design a behavior, a human would come in and try to write a reward function or a cost function, which I'm denoting by J over here. And then, of course, the robot has to obey the rules of physics, which I'm denoting by F over here. Now, once you try to optimize this, these real physics models under real constraints, this typically becomes infeasible. You can't do this in real time. So what we end up doing is, human comes in, uses their own intuition to construct these simplified models. One example is you could have a quadratic cost function and a linear, transition model known as, LQR, very popular. But of course, there are many other approximations, one could come up with, right? And, typically we end up optimizing such models for real world control. Now, while this works, as you were seeing in the videos before, such an approach ends up having, several limitations, right? And the real limitation really as a human has to think, per problem, what kind of simplification I need to make so that my robot works in that particular scenario. So, which means that if the robot goes outside the set of assumptions, the robot might fail. Scaling to many different tasks becomes quite challenging because if you are, say, doing jumping versus running, the assumptions you might end up making are different, which means the human has to spend quite some time, designing these approximations. And lastly, they cannot really fully leverage the hardware's potential. So one thing, one might say is that if you look at, computer vision, if you look at language, this is what people. This is what people would call as the feature engineering problem, where for a given problem, you'd have to develop a particular set of features, right? I mean, there was SIF, there was HOG, there were many features which were developed for, particular applications. So one thing we can ask is, at least in vision and language, we have evolved into a stage where we don't think in terms of what features I need to design for a particular problem, but we think in terms of, here is the data, here's the task I want to do, can I learn to perform that task, right? So we can ask the same question that instead of humans designing reduced order approximate models per task, can we automate this process? Can we make it less manual, more automatic? Now, once we start thinking in this particular way, the question ends up looking like we have some observation, we have some goal, and we want to produce an action. Now, at the very, very lowest level, where one is actually controlling the robot, you have to produce current or voltage. That's how we interact with the real world. Now, one could try to learn this block where you say, this is my observation, this is my goal, produce current or voltage. But the problem ends up being that, typically, one is outputting these currents or voltages at a very high frequency. Typically it's, tens of kilohertz that you're controlling. So this becomes quite a challenging learning problem, where even if you have to do control over 1 second, the amount of data you might need is huge, right? So typically, no one ends up actually doing this, right? So just for an example, if I have an image which is like this, and I want the robot to manipulate to go to a knot, finding actions at such high frequency is going to be infeasible, at least on most machine learning methods. So what we end up doing is, we develop, some abstractions. And, one thing is, we have a planner and we have a controller, right? And what this is really trying to do is to reduce the horizon of the problem and break it down so we can solve simpler problems instead of solving the full problem together. Now, I think different people might have very different definitions of what a planner and controller means, and these boundaries are blurry. So by no means think of my definitions as the definition. Is just my perspective that I'm presenting. So a planner, the way I like to think about this is something which has got to do with semantics, geometry, and kinematics. Kind of what is it that I need to do? So it's some kind of a motion description of what the robot needs to do. Versus the control, and this is what I call as the digital or the virtual intelligence, where you don't really have to deal with any of the physical properties of the world. Now, what do I mean by physical properties of the world? Things like inertia, dynamics, and so on, which are really important to apply commands in the physical world. So controller, in some ways, you can think about is something which is realizing the motion which the motion descriptor produced, right? And this to me is a problem of physical intelligence. How do you deal with the physicality of the real world? Now, where one draws this line, changes paper by paper, right? But almost everyone, draws a line, somewhere, right? And in some ways, if you think about use of machine learning, it's much easier to do machine learning for doing planning. And it's increasingly, harder and harder to do machine learning once we get to the lower and lower control layers. So, most works would have, some kind of a position, derivative controller or, some current controller running at the bottommost loop, and you're almost doing learning on top of it. So what I'm going to do in this talk is kind of, walk through how we have gone through this divide of maybe starting from machine learning applied to more planning and gradually moving down. Because it's important to move down to improve performance, to be more reliable, to be more robust. Right? But that's the story of the talk, and we'll walk through that, through some examples. Right. So first, let's think about the planning problem. Right. Um, and the first time I started doing this was almost 10 years ago, where we had this robotic system learning how to push objects. Um, and this was a robot at that time, a Baxter, which just interacted with the world on its own, running 24/7, just collecting data. It was really stupid in the way it was collecting data. Right? What it would do is it would, figure out a point on the object, and it would figure out the direction and by how much it should push this object. So that was the action space for this particular robot. Now, how is that action executed is part of a controller which was assumed to be given. Right? Now, the data looked at the following form. We recorded the image, the robot took an action, we got the next image. Right? That's the kind of data we are collecting to do some planning. Now, how did we construct the planner? It looked like if you have a current image, you have a future image after doing an action. At deployment time, given the current image and a goal, you would try to predict an action. Right? So what we learned was something called as inverse models, where we take the image X, process it through some neural network represented as f of y, same for the future image, and they go into an action predictor. Right? So you have the robot collect data, you get image, action, image, action. You take all of this data and learn this inverse model. Everyone with me? Okay, great. Now, what we showed was, these kinds of inverse models could be used for a variety of problems. So, some of it was, doing pushing, where we would have this current image the robot is seeing, and you would give it a goal image, and then see, what the robot would do. It would, push these, unseen objects, or, you could, give it, something else, to push some other objects it would do. But this was, some very simple, rigid object pushing. Then we, took this to say, hey, can we do maybe more complex, manipulation? And this is where we were trying to manipulate ropes. So here is a robot again playing with a rope in the same way, pick it up at some position, keep it at some position. Again, just learning how to plan in somewhat of an abstract action space. And then at deployment time, we could give the robot a goal image and say, hey, the rope is like this. Can you produce a sequence of image to get to this target, which is, tying a knot? And this is what the robot would, end up doing. Now, these systems were kind of working, right? I mean, the success rate was 20 to 30%, but even learning how to perform these motions, which are, pretty directed, was encouraging for us at least to say, hey, even on something like, rope tying, if the robot just interacted with the world and collected its own data, it could perform such tasks. The one thing, which, did become limiting, though, was that all the data over here was collected in the real world, and scaling this real world data collection is very challenging. You need tons of resources to actually scale this. So next we were thinking of, hey, can we consider alternatives to doing this, real world data collection? And, at the time, well, not at the time, but, I think Sangbei had this very nice video of this MIT cheetah, doing these very agile moves. And one thing again we thought is, okay, the controller looks really good, right? But this controller is working on this very specific scenario of jumping over these obstacles. So could we again learn a planner which could help this controller generalize to different environments in different scenarios, right? And this became a work where we said, hey, we're going to learn a planner, and this planner is going to be trained on many different terrains so that the robot from its perception could figure out what actions to take, right? So that we can go to new terrains and then generalize. So at the time, we used this MIT Mini Cheetah as an experimental platform. And the way we pose this problem is we would take a depth image and we would predict an action. But this action is again, a planner because we are just predicting how the robot motion should look like. It's telling, what the body velocity should be and what the contact schedule should be, right? And then it, goes to a controller, which outputs, joint positions, a PD controller, which outputs torques, and all of these things were already there, but these were all, fixed. Right? So what we did was we pretty much trained, the system to, perform actions. Now in simulation, these results, look nice, and you could get these nice looking gates of these quadrupeds, jumping over different kind of obstacles, kind of mini parkour, if you wanted to sit. Right? Now we also transferred these things into the real world, right? And the robots were, jumping in the real world. But we also noticed, there was a big, sim to real gap, which was happening. Right. So for example, in simulation, we could jump almost 1.5 to 2 times the body length of the robot. But in the real world, we couldn't get anywhere as close. And we were like, hey, what's happening? Why can't we cross this sim to real gap? And when we did that further investigation, what we realized is this model-based controller, makes the assumption that it is estimating body velocity. And while estimating the body velocity, it assumes that there is no slip between the foot and the ground. That's a core assumption which is made. Now, which means that if the robot is running fast, this assumption is almost always violated because your foot will always slip if you're running fast. And this was one of the main reasons why we were getting this, big sim to real gap in, this particular work. And of course, there are, many other, things which are, not modeled by the simplistic controllers. The motor dynamics may change, at fast speed, and there might be, many other factors which are not modeled. So the lesson was if you just learn to plan, your controller ends up becoming the bottleneck, and one has to, go down and, figure out how to make the controller also be more adaptive. Uh, so, so, so what we have discussed until now is that even if you put a lot of learning to just do planning, it cannot really compensate for the limitations of what the underlying controller has. And even today, we have these very good planners which come from vision language models. I'm going to show you an example which comes out of Google a couple of years back, where the input is I spilled my Coke on the table. How would you throw it away and bring me something to help clean? The robot says, I would. And this is using the VLMs at that point. So what we see is the robot has this common sense reasoning to say, it found a Coke can, it picks up the Coke can, it tries to put it in the trash can, but it cannot really put it in the trash can. It realizes it needs to get the sponge, it gets the sponge. So all of this cultural knowledge is there in these vision, language, planning. But the real question becomes is, can you actually execute the task, perform the task? And when it comes to clean the spill, this is what ends up happening. Right? So it's just reiterating the same point that, okay, we can do a lot of good machine learning on the planning side, but unless we move down this axis, having really robust and performant behaviors is going to remain a challenge. Right? So the first piece over here is, training some vision language models to do planning, right? And they can get us, quite far, but there's a lot that needs to be done. Okay. So how do we move, below in this stack? So one, popular approach being explored today is the approach of behavior cloning, which is going one level below the plans which come from these, VLM. And a lot of the work, at least recently, got inspired by the Aloha system, the work that TRI was doing, but also many other labs around the world, trying to see how we can have humans collect data and then train models on that. Right? And recently there have been these several efforts to scale up real world data collection. Now, the one challenge that one ends up finding in these behavior cloning approaches, at least today, is if you closely look at, when they're, showing generalization. So this is, for example, they might put a tape and say, hey, I'm shifting, uh, this object around the tape, right? So the amount of generalization that you're seeing is actually very tiny. It's maybe a couple of centimeters at most. You could, in theory, get more generalization, but then you just need more and more data for humans to collect data in many, many, diverse scenarios, right? And then if we, delve further into the literature and look at how these models are scaling. So this is showing the task of shirt folding, again from, this paper, Aloha Unleashed. And if you look at, this is the number of demonstrations, and this is the performance. So what you're finding is there seems to be some kind of performance saturation, already hitting in with the number of demonstrations, which is not too large. It's around 10,000, but it seems that getting beyond this 70-80% barrier is not straightforward. So what's going on? I mean, why are we hitting into some of these performance bottlenecks presumably? So, one thing you can say is, hey, we just don't have enough data. If you look at, GPT-4 or, image data, it was trained on almost 10 trillion tokens, right? I mean, a token is roughly a word. An English sentence has typically 20 words. So 10 trillion tokens would roughly be 1 trillion sentences, right? So one could try to collect, this huge amount of data. Presumably, if you did this, it would cost around 10 to $100 billion to collect this amount of data. And then if you change your hardware, it might, or you change your sensors, it might, you might still need to collect data again, at least with current methods. I mean, people are working on developing better methods, and the story in the future could be different, but this is how things, stand today. The other question, we can also ask is, okay, this data is expensive, but is this really the right kind of data to be collected? And to make this point, I'm going to link, how people are modeling language or the intelligence in the virtual world, and try to make a comment on why this kind of data might be insufficient for robotics. So if you think about language models, the way we frame this problem is to say, I'm going to eat and then I have to predict the next token. So suppose I have this sequence of tokens, S1 to ST, right? So now there's a policy which is trying to predict what is the next word going to be. Right? This is how language models are trained today. Now, if the action is chosen to be banana, which we sample from the policy, then we're going to generate the next sentence by just augmenting the banana to the sequence of words which were there previously. So in some ways, this dynamics model is completely deterministic. Right? Given the action, you always know what is going to happen next. There is no uncertainty involved when we are doing language modeling, when we are in the virtual world. But this is exactly where robotics ends up being very, very different. Right? Dynamics is not deterministic. It's very stochastic, but also it includes things like mass and inertia that you need to account for, right? Something is heavy, something is light. Those things need to be accounted for. And this is very well illustrated in this video, which Alberto Rodriguez's lab put out, where they did a very, very controlled experiment where they took this object and pushed it thousands of times with the same force, initializing at the same location. Even then, what they found was this huge variance in where the object would move, right? And this is really coming from the stochasticity, which is there when we are trying to apply actions in the real world. But the point being that you just can't take these approaches, which are built mostly for planning, and just apply them directly and hope everything is going to work out, because we still have to account for the stochasticity. We want to account for the dynamics. Now, where does this show up? Right. So now let's look at some videos which have been put out recently. So if you look at this robot trying to place an object, it's placing it at the right location, but it almost never wants to touch anything. Right? It's almost like afraid of making any contact. That's because it doesn't wants to deal with the dynamics at all. It's a purely kinematic motion which is happening. Right? Then, if you look at some of these videos of laundry folding, very impressive into what one can do, trying to fold laundry, directly from RGB perception. But if you look at this video, I mean, sometimes things work very well. Other times when the robot is trying to say disentangle these pieces of clothing, it keeps losing this grip. It again has no idea of the dynamics. It's purely a kinematic motion which is happening, right? So in some ways, you should really think of behavior cloning more of a planner, not really a controller. It's kind of telling you what motions to do, but it's not smart enough to tell you how to execute those motions. You're relying on some baked-in intelligence to do it. If that intelligence isn't there, it isn't going to work. Right? So what we decided was to investigate this a little more and say, hey, how can we go beyond and try to bake in more intelligence so these planners' performance can improve. To do this, we took this furniture bench task, which is a long horizon problem where you need to take these multiple parts and put them together to do some kind of assembly. So the first thing we did was because a lot of this work also was in simulation, which meant that we could collect large amounts of data, and then we showed some sim to real time. So but let's stick to what we have over here. So we trained a diffusion policy, and what we found is the success rate with the number of demonstrations. What we found is the success rate of this behavior cloning policy was saturating. And the way we collected data is, you would give a demonstration, and then you would keep on giving, up till 100,000 demonstrations, do pure supervised learning, using diffusion models. Okay. Now, if you have done behavior cloning, you probably have also, learned about the fact that it's very easy for the policy to deviate from its distribution. And therefore, people need to come in and give corrections, right? Which is what people do with Dagger. So if you don't just give a passive data set, but if you are there to generate more trajectories online, depending on where the robot is doing bad, the performance improves. And with Dagger, you start getting closer to 80% performance. Right? But again, now doing Dagger, at scale can actually be quite challenging to do. Second, we looked at what are the kind of issues which are happening, and why is the robot's performance not as good? right? And what we found was that there could be some very small errors which can happen. For example, you're carrying this part to insert it. If there's a small misalignment, the planner will not recover from it, right? It will just fail. Or if the object was picked up in the gripper in a bad pose, you wouldn't really recover for it. Or so I mean, these kind of small things, which if they end up happening, the planner cannot correct for it. And one of the reasons this is happening is that if you look at the current literature in behavior cloning, what people are predicting is not just one action, but a sequence of actions. So they might predict 8 or 16 actions, and this action chunk is essentially an open loop, right? So for almost 1 second, you're executing 8 to 16 actions. Now, if something bad happens, within that time period, you cannot correct for it, right? That's a fundamental problem. So what you can think of is what behavior cloning has done is it has taken VLMs, which were planning at the level of maybe 10 seconds, and reduced it to planning to 1 second. So it has moved us down, but not down enough where we can end up, getting reliability. So what we did in this work is, we trained a residual policy, which took the plan from the behavior cloning and then used reinforcement learning to correct these plans at a much higher frequency, right? I mean, over here, the high frequency is still not that high, it's still 10 hertz, but it is going one level deeper. Now, if you end up doing that, at least on these kind of, benchmark problems, the performance ends up being, much better. So, these results are, first in simulation, when you transfer them to the real world, there's still some gap, which ends up coming. But at least it kind of gives us an intuition behind why the behavior cloning's performance was saturating and what needs to be done to actually get to reliable performance eventually. And this is something we observed, across the board on many different tasks that we, tested this on. So, what's the moral of the story? The moral of the story is that we need to go more down. And, we started with VLMs, then we did behavior cloning. And, if we can then go down more on the control side, maybe using reinforcement learning, then, you can get, better performance. I'll pause here for a bit. Any questions from anyone so far? Yes.
Do you think it's like inherently like, very scientific that we just for evaluating those big models, we just need to predict something over 10 seconds. Every 10 seconds to kind of plan. We just see like correlate why one thing works better than the other.
Yes, I don't think it's an inference time problem. I think it's more of a data problem. If you want to do more long horizon things, the amount of data you would require is going to be much higher if you try to make more frequent predictions. So I would not think this is a problem because these models are large and therefore they're not able to make fast predictions. Yeah. Cool. So what I'll do is I'll continue my journey, down to see how can we make, make more progress, improve performance of our robotic systems even more. And, the North Star, at least in my view, is, being able to perform, dexterous manipulation, kind of things that you're seeing on your screen, right? And a lot of these tasks, involves picking up an object, then getting the object in the right orientation, and then doing some, downstream, problem with it. Now, to study these, family of problems, we started with one instantiation of dexterous manipulation, which is doing in-hand reorientation. Right? So we have the object in the current state, and we want the object to go into some goal configuration. So now, given a model or a simulation, given an action, we can predict what the next state is going to be. And there's a way to set up the problem where this is the cost we want to minimize, which is how far is my end state from the goal state, subject to, constraints from physics. Right? And, if you look at, performing, in-hand reorientation, this involves, frequent making and breaking of contacts, as you just saw in the video, which means it's a continuous discrete optimization problem. Again, hard to solve, so what people, typically end up doing is we end up making simplifications, right? I mean, you would assume that the object shapes are simple, so we can, solve this problem. or we assume that you only rotate in a small range so that you can linearize the problem, or restrict the finger motions in some way. These are all assumptions which are made to somehow simplify the control problem. So then, around, I think in 2017, 2018, OpenAI decided, oh, we don't want to do things like this. We want to just learn the strategies automatically. And this led to the reorientation paper, which was presented, in 2017, 2018, reorienting this cube. Now, but if you look at the system that they built, the system looked like this, right? So there's one hand, surrounded by these gazillions of camera, you know, not ready to be deployed in the real world. It pretty much only worked for a cube, right? Not really any other objects which are there, right? And if you looked at many reorientation systems at the time, in all of them work with a few objects. All these objects are very simple in shape. They are mostly convex. They don't generalize. And then all of them are working in this configuration when the object is supported by the hand, right? Which is much easier of a problem than if the hand was, facing, downwards, because then the object is almost always unstable as you're trying to manipulate it. So what we decided to do was to say, hey, can we go from this highly impractical system to something which is much more practical? We had this, one camera looking at this, this hand orienting this object, everything open source. We can get this whole setup in less than 5,000, as opposed to more than $250,000 setup or even higher on the left. We wanted to work with complex shapes and also, generalize to new shapes that, were not seen before. So for this, we tried, going down the reinforcement learning route, work led by Tao Chen, where we were training in simulation. So we would give, these many objects to be reoriented in simulation. And then the question was, could we learn in simulation first and then transfer these policies, into the real world? So how did we go about doing this? So, ideally, what you might want to do is you might say, hey, my robot has observation to some images, maybe, depth observations. We have access to the joint positions and the goal pose in which I want my object to be. Let's learn a recurrent, RL policy to produce, actions. Now, and we define a reward function, which is how close you are to the goal configuration. These kind of policies, if they are learned, they can be deployed, but are very, very hard to train, at least directly from perception. And I guess probably many of you already have experience, doing this and finding this is, extremely hard to do. Right. The other thing, which again, I'm assuming many of you are familiar, is you could use privileged state in simulation, which is very easily available. Things like, joint velocities, the current pose of objects, the object goal pose, so on and so forth. Easy to train, but, cannot really deploy. So I'm going to walk through this part, slightly quickly, because I'm presuming a lot of you know about teacher-student learning. But, if any one of you wants to ask more, just, ask me more. So the first thing we're going to do is to train this, policy with privileged information using RL, right? So how did we set this up? We defined a state space, which includes the joint velocities, includes properties about the object, and, about the goalpost. Note that we did not include any information about the shape of the object. This is really including kinematic properties of the object over here. And the policy, the action over here was change in the joint positions. And so we would get, given the action, the next, joint positions. And the rewards were, how close you are to the goalpost and other shaping terms that we will look, later at. And then we trained a single policy, which would work across, hundreds to thousands of different objects. And this was trained, using, standard, PPO at the time. So the first thing, we noticed was, if you look at these policies in simulation, they were able to perform, reorientation of, diverse objects. This is showing one, and this is showing, many other objects, being reoriented. right? All of them coming from a single policy. And one of the surprising things for us was that, all of these policies are operating without knowing the shape of the object. Right? They're just operating from pretty much knowing the object pose and then doing actions, based on that. And this was actually key to, train the teacher. Otherwise, he would not have been able to train the teacher if the teacher required more shape information. Right. So first we trained the teacher, using RL, and then we had a student policy which was trained, using supervised learning, using Dagger. Right. So standard, teacher-student, paradigms that we used. And then, for real-world deployment, we would end up using the student policy. So how did the system look like? You would get a point cloud, join positions to the controller, which is an RL policy, output join commands. And this is how the setup looked like. And the evaluations I'm going to show you are really on new objects the system hadn't seen before. So here, this is a real sense camera, running at 12 hertz, uh, or the policy running at 12 hertz. We give an object, and we want the object to get into the orientation shown on the top right. And this is how the system takes the object and orients it into the target configuration. Here is another object, which is being reoriented to the goal orientation. So these are lab demos, right? So these are nowhere close to 100% perfect, right? But at least it's showing you that, we can, even for this more complex manipulation problem, where contacts are much more important, we can, train these policies with RL and then transfer into the real world. So what were some key things which were important to, make this work? Of course, one was this idea of teacher-student learning, which has been explored in, many works. There were some other things, which, were important. For example, we had to speed up, point clouds based training, because if you train with just point clouds, it would take us 20 days on a single machine. So we did some changes to make this fast. Other was to run these policies in the real world. Again, there were architectural changes required. We couldn't really do point cloud processing, so we went down to sparse CNNs. Then, we had to learn good actuator models, which was, quite important to get the system to perform. And then there were, a couple of other things, reward shaping and hardware considerations, which I'm, happy to talk about, later. So I'm going to skip. Well, I'll talk about this. So one interesting observation that we also found while doing this work was that commonly, if you go and talk with control people, and they would say, hey, if you have more degrees of freedom, it's a hard problem to solve, right? So, what you might say is that, hey, as I'm increasing the number of fingers in the hand, the control becomes harder and harder to do because there are more variables to optimize for. But, I think what we found was, something quite the opposite, that as you increase the number of degrees of freedom, the performance of the system actually improved, right? And it kind of makes sense in, hindsight, because if you have more, fingers, that means there are more ways in which you can manipulate the object, and the object is, still stable and does not really falls down. So in some ways, for machine learning systems, number of degrees of freedom is not a bad thing. It can actually help optimization. It's the same thing that people find with deep networks. If you have a deeper network, it might be easier to optimize than a smaller network that you're trying to fit. Right. So at least what we believe is over parameterization is a good thing. So having more actuators is a good thing. And it can actually make object manipulation be much easier than having fewer number of actuators and then trying to do manipulation, which would be quite a different view if you're coming from a heavily model-based, line of thinking, where more actuators are not necessarily a good thing. Then, we extended this to, doing more fun things. So over here is, trying to peel a vegetable where we're rotating the squash so it comes to the right orientation. Then the second hand comes and, peels it. But the peeling is something which isn't, trained, via simulation, but everything else, all the reorientation part is. And if you look at this hand, it's trying to hold this object in place despite, forces being applied on it. It does work for different objects, there's still a different cylindrical object. It would be cool if we can, make these things, work on a ginger, which would be a very fun project. But I have not been successful at convincing anyone to go to a ginger yet. But hopefully, we will end up going to go to a ginger, at some point. Now, I think this adds to an already existing, rich line of work. A lot of it, which was also done at ETH, showing how, sim to real reinforcement learning is a very powerful paradigm of, learning controllers. So, I mean, the sim to real paradigm is great because if you learn an RL controller, it's like incredibly robust. It can generalize, but you have to construct simulation task by task. So it's not as easy to scale it to diverse tasks as behavior cloning is, but it gives you something which is, much more performant. So, I mean, our lab also does, some work on locomotion, which I'm just going to briefly show and not really spend too much time getting into it. So one thing we were trying to do was how do we speed up locomotion? And one of the problems which ends up happening is if you want to run fast and you want to spin fast, then most of the commands you're giving are infeasible. So how do you ensure that you can both run and spin fast with the same policy? Or, sometimes the robot would go outside, a screw in the motor, for example, would come out. Yet, this robot would be, robust and, keep on moving, thanks to a lot of randomization, which is happening in simulation. Or, a robot, dribbling a soccer ball on ice, everything running, on board of this robotic system. And, from there to performing these, more exciting, whole body tasks where to throw this ball, the robot has to use its whole body to, perform the motion. Or if you were, to, drag heavy things, again, to use the body to apply the requisite amount of force to perform the task. Now, everything again, trained, in simulation. And sometime, trained, uh, too well, I would say. So over here, these are some, bad things which can happen where you just hit the limits of agility and the system, fails. This is some work where Tiffany was also involved when she was at MIT, where you can also control the stiffness, of these, manipulators. We can make it stiff, we can make it light. Once these things are working, we can do some high-level control using a Apple, Vision Pro, and then you can get the robot to perform more tasks by giving high-level commands. But the low level is now trained, using RL. And more recently, been expanding to humanoids. We don't really have a paper on this. This is just work in progress. This is showing just some first videos of walking that we are starting to get, but more to come later. So this was a distraction. So let's come back to manipulation, right? So what I showed you in terms of doing this in-hand reorientation, the system was not perfect, right? And the objects drop, many times also. And you're looking at, hey, why is this happening? So one of the reasons is if you're just doing these things from vision, you don't really feel the object slipping out of your hand. So the next question was that, hey, it's that's not good algorithms, but we also need, more sensing. So could we incorporate, touch sensing into these robotic systems? And so we had a work where we're trying to simulate, tactile sensing. So here you're seeing the tactile fields being simulated so that we can then go and perform, sim to real, with tactile data. And what we showed is that, we can do these problems like putting the peg in the hole in simulation and then go back and transfer these algorithms in the real world. also with tactile data. Then we said, okay, now we know how to deal with tactile. Let's go back to the problem of reorientation, where I now want to reorient the object, but now using tactile information also. This is showing the shadow hand with the green and the red things are showing where the contact sensing is activated, and green is where the contact sensing is not activated. This is a very coarse, contact sensing, which is there. And we can start doing, some reorientation, just with, tactile sensing. But you also run into, exciting machine learning problems. So if you look at the teacher-student learning, this teacher-student learning paradigm no longer, works or doesn't work as well. The fundamental reason being, if you look at the teacher knows the position of the object exactly. It knows the pose of the object precisely. If you had vision, you could also get the pose of the object from a single observation. But if you have tactile, you need to do some exploration to figure out what the pose of the object is. It is not inferable by just looking at a single observation, which means that the teacher has too much information and the student has no way of matching this. Right? The student needs to do exploration, it needs to deviate from the teacher, do some information gathering before it can go back and match the teacher. Right? So this is the problem which runs into, right? So if the teacher is too good, you can't mimic it. Right? The other problem is if the teacher is suboptimal, then you can't go beyond the teacher. Both of these are problems when one ends up using the teacher-student learning paradigm. So typically what one might do is to say, hey, I'm not going to do teacher-student learning. I'm going to put a reward function R plus lambda times the teacher and then try to learn from it. But then you run into another issue. Who's going to tune this lambda? Right? And this lambda tuning is problematic. Right? I mean, if you could tune it, you might do better than either RL or imitation learning, but tuning it is a problem, right? So then, we were looking at, how can we resolve this problem and have a more principled way to end up tuning these terms. So we came up with a method which automatically tunes this lambda. It also tunes this lambda at every time step. So at every episode, the lambda will get updated as the training goes along. And the idea is, only use the teacher when it is actually useful. Now, what does this mean? It means that, what we do is we learn two policies and make it a game. So one policy is only being trained with the reward function, which we call as pi RL. There's another policy, which is being learned, with both RL plus imitation learning, which is pi RL plus IL, right? Now we make these two policies, compete with each other, right? And the way we make them compete is to say, if we measure the task reward, then only use imitation learning if the task reward obtained by those joint policies is more than the task reward obtained by only the RL policy. Therefore, this constraint ends up being, coming as a dual variable when you set up the optimization, and then you get a learning schedule or an automatic learning way of tuning the lambda. Right? Now, I don't have time to describe how the dual problem is set up, but if you're interested, all the details are in this, paper, teacher guided reinforcement learning. And what we find is, as opposed to the raw teacher-student learning, which is not as good, you know, we end up doing, substantially better than just putting, simple teacher-student learning. Now, I should end in a couple of minutes, I presume. Okay, I'll be good. So this problem, appears in many places. It's not just when you have, H or a heuristic reward as, this feature imitation. It could happen as energy. It could happen as, other kinds of reward shaping that, people end up doing. Right. And probably all of you know that reward shaping is everywhere, right? It's there in pretty much every sim to real paper. So the question really comes down to is, can we do something better than manually tuning these lambdas? Can we improve beyond it? So we expanded this work where the high level idea is, if you only train on the task reward directly, you almost never end up getting good performance. If you use some heuristic, right, such as reward shaping, the performance improves. But again, you have to tune this lambda. This lambda is stationary over training, not that good. Can we do better than this? Right? And the answer is yes, you can. Unfortunately, I don't have time to delve into it, but the idea is fairly, on the same lines as we did with the TGRL or the previous paper, where we make two policies, compete with each other. If you're interested, you can read this paper, Going Beyond Heuristics by Imposing Policy Improvement as a Constraint. And there's some, fun things you end up getting. For example, if you use the heuristic as energy, then this quadruped automatically learns these kind of behaviors such as squatting, because the squatting conserves energy. So you don't have to teach the quadruped to squat, but it will automatically figure out to conserve energy, it should squat, right? So these things are quite exciting to see, at least, they emerge. So, and if you took, if you went to ISEC Gym or any of those, benchmarks, you took a heuristic reward which people have designed by hand, but if you use our tuning, you would at least get 2.5x better performance on average, right? Because it tunes these heuristics better than what current methods are doing. So, please check it out. And I will skip and I'll try to end in, 2 minutes. So I talked about, how we were going down this track and we were discussing about reinforcement learning. But, eventually, we run into other issues, and the other issue is hardware considerations. If we don't have the right hardware, no matter what you do, the learning cannot compensate for it. Now, what do I mean by this? A good analogy is the following. Suppose you had a truck which was trying to move a chair. What would happen? The truck has to move really slowly, right? Because if it moves fast, the chair is going to just fly out. It means that you need to match the inertia of your manipulator with the inertia of the object that you're manipulating. You need to have high bandwidth so you can close the control loop fast. If you don't have those things, manipulation will never be fast. It will never be dynamic. And this is what's happening with most of manipulation today. This is an image to think about. It doesn't happen in locomotion, because in locomotion, you're always on ground, and it doesn't matter because the ground doesn't move depending on the force you apply. But in manipulation, the object does move. Right? So actuators need to respect physics, right? So what we want is really low inertia, high bandwidth, high torque, be transparent. And there are many ways you can do it, right? For example, the animal has to use elastic actuators with torque sensors. There are other tendon-based actuation schemes, which I think a lot of, in Robert's lab being developed by also, exciting things over there. One could have soft and compliant hands. And the thing that we have been pursuing really is a direct drive, quasi, direct drive hand, which can have these properties, right? So, we started with a small finger to, begin with. And this is showing first, our finger, which can say go under the plate, lift this thing up and place it. Or if you wanted to, pick up these very, very thin objects, these fingers had a 4-bar linkage, so it could comply and then, pick up the object. Then we took to a next iteration of this hand, which we call as the eyesight hand. So now it has, 3 fingers, roughly designed to human proportions. We can discuss if this is a good idea later. But this is how the hand looks like. So it's a 3-fingered hand. But this is the first iteration of it. Now, if you look at how this hand moves, so this hand is super compliant. So if it is, hitting a table, it won't break the table. The hand will comply to it. So you can actually do control where contacts are your friends, and you're not afraid of, making contacts with them. And this hand is also, fast. As you will see over here, we throw a bottle, the hand can catch it. And this hand is, covered completely in tactile sensing, which is a gel side sensor. So if you're interested in, studying how can tactile sensing help your manipulation, it's also an excellent, platform to, study, those kinds of problems. So for example, if you were to train the vision policy to open this bottle cap, you will not be able to feel the ridge. right? Because at some point you just can't, and the policy fails. But if you were to use, say, vision plus tactile, which the hand provides with, you can do more interesting, manipulation problems. So one thing we can all do is to do sim to real RL, and that would be exciting. But also, I know many people want to do imitation learning. So we also made what we call as a dexterous exoskeleton that we can wear, and then use this hand to collect data. So you can collect data which is both vision and tactile, uh, for doing interesting, complex, dexterous manipulation to kind of show you where we think, things can be. So this is just showing the potential of what the hardware can do more than anything else as of now. And this is trying to assemble the finger itself, because all of us like to have robots which can build, themselves over again. So it puts a screw, you know, uh, takes a drill bit and it will, try to, drill the screw, right? Showing that, these kinds of, fine manipulation is potentially possible. And I think some of the constraints are coming more from a learning perspective. Or I'm going to skip this, but even if you want to pick up, things like a coin over here, you could go, pick up a coin. And I'll stop with this video. I'll let this video go, but also happy to take any questions. But the main message being, we need to go more down. We'll complete the main message. We need to go more down in the stack. The more down we go, the more fine and dexterous and robust control we can do. So I think we, as machine learning people, need to push machine learning down. And if we have the right hardware, it really enables machine learning to happen in a more fundamental way, in a more easy way. The more we can reduce this requirement of operating at high frequency, with some of it we can do by building the right hardware, we can put machine learning in the overall stack. So with that, thank you so much for your attention. I will let this, video play, and I'm happy to take, any questions. Yes.
For the top, when it's in Excel, is the operator having a haptic feedback on the touch?
So it's not from the touch, but the linkages which give you proprioceptive feedback.
Like a touch in sensing that the
No, so there is
is the operator.
no, so there is no, so what you get is, so if you see there are linkages which are connecting, so through the linkage, you get a proprioceptive feedback, but you don't get any touch feedback. There's no high resolution touch. It's very weak proprioceptive feedback that you're getting.
Right, because these problems, there is always a problem with these operational setups, right? Like
Yeah.
when you learn the operator
Yeah.
compensates for those missing things.
Yeah.
Somehow differently.
Yeah.
You learn not really how they can do that.
Yeah. Yeah. So I think the one thing we tried doing was to build this thing so you get some coarse force feedback, right? So if you think about it, if you pull your finger, a lot of the forces you feel is actually on your finger joints, right? So that's kind of what we are getting, through this. Now, the other question is it sufficient to learn a closed loop policy, right? Which is a good question, right? And this is why we're collecting data with tactile. So we can ablate this now to say, if you don't use tactile, what is the performance of the policy? If you did use tactile to learn the feedback controller, what is the performance? So we don't have those experiments yet. If everything goes well, maybe in 2 weeks we might have them. But that's a fair point, and that's something we want to investigate with this platform. Yeah.
One question is, even the human can do this without tactile sensing, isn't it showing that maybe just a joint kinetic force feedback is enough for this task, at least in this level?
Yes, I think as the point was made, right, that humans are also doing a lot of compensation. I mean, how good is your feedback policy? I think is a whole, different question. So I think it's still to be seen. But at least I think it's evidence that you can at least teleoperate quite a lot with just, some proprioceptive feedback. So ideally, a machine learning algorithm should also be able to do it. But I think it's, TBD.
Other question is, when you said.
Yeah. Which one?
The graph with easy for ML and.
Oh.
how do you-
This one, yeah.
So what do you think it is harder for ML if you go down? Is it because of the lack of data or because it has to control some state? That is, instead of just predicting the next thing.
Yeah, so I think the one thing is if you're doing, so you can't do really imitation as you go down because you just can't move the robot so fast. You just have to do RL or some other optimal control, but not imitation. But if you're doing RL, then your episode lengths are really long. Then that becomes a long horizon RL problem, which is also hard. So the question really then boils down to is how can you make the problem easier for ML? But that's a fundamental reason. And then you're really dealing with contacts. So if anything is wrong in your simulated contact models, the lowest level of the control stack will not be as friendly as some of the upper levels control stack, might be. So that's why I think, it's harder to, control at high frequency. I don't think it's got anything to do with how big the model is, because I think we will figure out ways to make models run very fast. That, in my opinion, is not the reason why ML is high. It's just the learning problem itself would be hard. Yeah. Yes.
Do you think that in get the recipe, you need to have all of these different approaches at the same time running different DNNs for like reasoning and like spatial reasoning and like RL residuals and like highest frequency, or like you think we have to figure out which one is best and just equal.
I mean, I think it's going to be hierarchical in some form like this. I mean, if there are hardware, if the hardware is not back drivable, if it is not um, compliant, or you can't change the compliance, there's nothing you can do with learning to compensate for it. And I mean, you could, maybe then you run the loop at even very high frequency, and even the system is not back drivable, you could do it, but then the machine learning problem becomes really hard. So I think having a good hardware from a dynamics perspective will make your machine learning be much easier. And in the same way, right? I mean, even if you're doing planning, none of these, units are so independent of each other. They all depend on each other, right? So I'm not advocating that we should think of all of them in isolation. I guess the point I was trying to make is that a lot of the learning has happened at the highest level, and the lowest level is, what is, where everything is pretty, hand coded. And the more we go down, the better the performance ends up becoming of systems. And there are, fundamental challenges which need to be addressed in going down. Right. And of course, I think there's some people who are going to take each of these elements and make them better. Like they're going to be better behavior cloning methods, better RL methods, better hardware. I think all of them are important. I guess my message is go down and do learning as close to the hardware as you can. And that will give better performance. Yeah.
How do you think would you about explanation from is it like we see that people collect a lot of data and try to fit a lot of behaviors, but it's still quite unique at the result.
Yeah.
Right.
Yeah. So I mean, I think a lot of the, say, so for example, the reinforced, like, I think a lot of the local corrections, or if you look at the work I presented where we're combining BC plus RL, a lot of those interactions are quite local. Right. So you could even presume that they should only be based on forces and not even on camera images. So those things can hopefully generalize across tasks, once they are trained. A lot of the scaling across tasks could happen at the behavior cloning and the VLM level, where you kind of get, reasonably good plans and lands at some high frequency or higher frequency like 1 Hertz. And then you have some control layer which works below that. And because this control layer has access to less high dimensional observations, maybe it can become, quite general. So at least that's how we see it right now.
Yep, there are no more questions, so we can conclude here. So last chance for questions. Is there any question from online? Okay, then I think it's pretty clear. And thanks a lot again for Professor Pulkit, Agrawal, and thanks a lot to you.